Today, I will talk about enhanced weathering of basic rocks, an effective process to reach net zero emissions. This is all about climate change, because scientists have shown that the Earth is warming up at an unprecedented rate since the beginning of the Industrial Revolution. They've shown that this is caused by an increase of CO2 content in the atmosphere, resulting from burning fossil fuels. CO2 content has been relatively constant in the last million years, resulting in a proliferation of life. However, this life is now threatened by the sudden increase in temperature. Various technological methods have been developed to decrease the CO2 content in the atmosphere. The efficiency of these methods will be evaluated, and it will be argued that more natural methods have been insufficiently explored. Here we are showing this unprecedented rate of CO2 increase. In the last million years, this is the increase since the Industrial Revolution. This is the detail of this part of the graph. So it's especially this sudden rate is the concern, and is causing the increase in temperature. At the time of the creation of the Earth, the atmosphere was around 90% CO2, as it is now on Venus and Mars. The CO2 went from the air into the oceans, then it was precipitated by organisms and dissolved as calcite in carbonate and became part of the rock cycle. In the Cambrian, 570 million years ago, the amount of CO2 in the atmosphere was 0.4%, and now it's 0.04%, or 420 ppm, which means that there is 750 gigatons carbon in the atmosphere. The rest of the carbon is stored in vegetation, soils, fossil fuels, oceans, and especially in rocks, 66 million gigatons. It needs to be realized that 1 gigaton of carbon is 4 gigatons of CO2, and 1 gigaton is 1,000 megatons, and 1 megaton is the weight of 1 million VW Golfs. Each about a ton. So it's all about the carbon cycle. And we are showing here the fast yearly carbon cycle. In black are the different reservoirs in atmosphere, vegetation, soils, oceans, and fossil fuels. But every year there's a large cycling of carbon between the atmosphere and the vegetation and soils, and between the atmosphere and the oceans. There is generally a larger intake in the vegetation and soils and into the oceans, but this is offset by the burning of fossil fuels by humans. And it's yearly 9.3 gigatons of CO2 that goes into the air. And of this 9.3 gigaton, 25% is used by vegetation, photosynthesis, 25% is absorbed by the oceans, causing acidification in the surface ocean, and 50% stays in the air, causing the increase in temperature. There's also the slow carbon cycle. This is the carbon that's 200 megatons per year, that's at the bottom of the oceans, go into the sediments because of organisms and become part of the slow carbon cycle in the slow rock cycle. So about 200 megatons move through the rock cycle per year. These are again the different carbon reservoirs. We are showing in red the effects of the burning of fossil fuels, so being the increase in the atmosphere. It's in the vegetation and soils, it's not so much of a decrease, but there's been also increase in the oceans, acidification. But there's also weathering, and we can use the weathering and enhance the weathering in carbon uptake and making it part of the rock cycle. That's what we'll be talking about. So if you look at global CO2 emissions in 2019, 80% of the greenhouse gas emissions are from CO2. The other ones are of lesser importance. So in total, burning from fossil fuels was 37.1 gigatons, transport, electricity, industry, heat, agriculture. But then also the burning of wood and other flammable materials caused by forest fires, wars, etc., needs to be added, as Greta Thunberg has said. It's 8 gigatons. 7 million people exhaling has to be added, as well as 769 million pigs, 238 million cows, and other animals. The emissions of the volcanoes, and in total, is almost 49 gigatons that has to be taken care of. So in 2015, the Paris Accord was signed by most nations, and the goal was to have 50% reduction from 1990 emission levels by 2030. Different countries negotiated different parts, but according to this formula, Canada would need 363 gigatons reduction. Now, the Canadian government in 2015 negotiated to have the reductions from the 2005 level. And so this was government at that time negotiated to have 30% reduction from the 2005 level. So the official goal should have, according to the 50% from 1990, should have been 224, going to 224, but this was the government in the last election. The Liberals promised 45% from 2005 levels. The NDP promised 50% of that same level, and the Greens 60%. So the Greens were the closest to the Paris Agreement, which in reduction from 2005 would be 61%. But Canada, as a cold country and a petroleum producing country, was able to negotiate. So these are these numbers again. A reduction of 363 megatons of CO2 emission per year is needed instead of 184 promised by the Canadian government. twice as much reduction is needed to be in line with other industrial nations. So what kind of action plan do we have for 2030? Well, it's agreed that all the coal-fired power plants will be phased out. This would obtain 20 megatons CO2 emission reduction per year. That all cars would become electric, resulting in 10 megatons CO2 reduction per year. Increase could be done in solar and wind power from 6% to 35%, as in Germany, which could replace the present electricity produced from coal, oil, and gas, and could produce 90 megaton CO2 emission reduction per year. Geothermal energy generation could reduce CO2 emissions by 10 megatons. Possibility of the storage of 50 megatons of CO2 per year, carbon capture and storage, so 50 Shellcrest projects. The amount of hydro and nuclear could be increased, but hydro is already high and nuclear comes with lots of problems. Biogas such as wood is dirtier than burning coal, making it inefficient, but biogas from waste could be used. Green hydrogen could be used, but would need the electricity that's already got reductions. And blue hydrogen can only be used during the transition. So these plans could result in a reduction of 180 megatons CO2 emission per year, something was promised now, but it's leaving 183 megatons of CO2 emission per year unaccounted for. And we'll look for solutions for that. So let's look at the efficiency of the carbon capture and storage in Alberta, in saline aquifers and salt caverns. For example, here is the Shellcrest Project, where the emissions from the Shell Scotford upgrader are transported to Redwater and injected in wells. So every year, 1.2 megatons CO2 is captured and stored by the Shellcrest Project, a great engineering feat that Canada can be proud of. Those are 1 million VW goals. This is 79% of 3 syngas streams, which represents 35% of the Scotford upgrader CO2 emissions. So 65% still goes into the air. So 100 goals per hour go underground. Great engineering feat. So governments all over the world are considering permanent storage of possibly 6 gigaton of CO2 per year, with a cost of 0.6 trillion per year, based on $100 per ton of CO2, on advice from the IPCC, which is 13% of yearly emissions. So it will not do everything. Oil and gas resources before production represent a small part of what was generated and stored over geologic time. Geologists know this. It is thought that the rest of the resources migrated and then leaked out. Therefore, a large part of stored CO2 might leak out in the future, say in 1,000 years, making storage ineffective. Hence, what further action can be taken to address the large emission reduction deficiency? Well, we could increase the natural geological storage of CO2 by enhanced weathering. It's an important part of this presentation. We could also increase the uptake of CO2 by vegetation and soil, cutting less forests, and increase the energy efficiency. Increase natural geological storage of CO2. The storage of CO2 at high pressure in depleted gas fields or saline aquifers is not natural geological storage and might leak out. The capture of CO2 happens in geology naturally by the weathering of basic silicates. The resulting bicarbonate solutions are transported to the oceans where they are transformed into carbonate rocks. This rock cycle is the ultimate sustainable geological storage of CO2. Sasha Wilson at U of A is researching enhanced weathering in Canadian ultramafic rock mines. The American project VESTA is pioneering technique of enhanced weathering of basic rocks to remove at least 1 gigaton of atmospheric CO2 per year. The American project Heirloom will be removing 1 gigaton of CO2 per year by 2035 at $50 per ton using enhanced weathering. Enhanced weathering has the potential of 500 to 5,000 gigaton CO2 reduction. So very good potential. The natural storage of CO2 by olivine is already happening on an Hawaii beach that has olivine sand in the beach. So 1 handful of olivine sand is sequestering CO2 today. This is an ultramafic xenolith from Australia. All the green ones, minerals are olivine, and this is the most common mineral on Earth. So only 0.101% of this olivine is needed. We can increase the uptake of CO2 by vegetation and soil, and here I'm planting a tree in my yard. We can also increase energy efficiency. This is very much necessary. And these emission reductions seem difficult to attain without energy efficiency actions, such as recycle, reuse, consume less, drive and fly less, increase public transit, cycle and walk more. Conclusions. Storing CO2 underground in gaseous forms, carbon capture and storage, is a temporary, inefficient solution. Yearly total global CO2 emissions are 49 gigatons and not 37 gigatons, as is most times assumed. 363 megatons of CO2 emission reduction per year for Canada by 2030 is a difficult task, and reaching net zero is even more difficult. Enhanced weathering is cheaper and more efficient than carbon capture and storage. Increased funding for research on enhanced weathering uptake by vegetation and soil and energy efficiency is needed. Human action made a difference to this starfish when it was thrown back in the ocean by the star shoal. Every person can make a difference. Spread some olivine sand, plant a tree, conserve energy.